in weathered or highly jointed rock mass, the failure plane may be less controlled by a single through-going discontinuity. So if you have a highly disjointed or highly jointed rock mass, the failure planes may be less controlled. It becomes difficult for you to control the kind of failure that is to occur. Then analytical procedures for such slopes tend to be similar to those for soils, and we are not doing soils. And so what we just want you to understand is that these principles we are going to use also apply for that of soil. So assuming you want to take a short course, you get some basic understanding here, and you happen to take a short course on geotechnical engineering, as in soil mechanics or civil engineering, then the principles are the same. Then the most important requirement for rock slope is to determine the correct failure mechanism. So you have to understand whether your failure that is usually happening or likely to occur, is it going to be planar? Is it going to be plane, or is going to be wedge failure, or is it toppling that is going to occur? Okay, so you need to understand, or you have circular failures. So if you get to know that these are the type of failure mechanisms that are likely to occur, then you study the mechanisms that attribute or that bring about planar failure, wedge failure, or toppling failure. If you get to know that this is what is likely to happen in my situation, then you take note of the mechanisms that are used in computing for this. Then this will generally demand a specific site investigation to evaluate the geology of the slope, the properties of the rock, the characteristics of the discontinuities, and the groundwater conditions. So indirectly, we have mentioned the various factors that you need to look at for. So the geology of the slope, which you might have gotten some information about the geology of the area, but now you are narrowing it down to that section where you are constructing your slope. What is the geology of that place? Then the properties of the various rocks there. And then when you know them, what are the discontinuities that are likely to occur at your cut face? And then lastly, you have your groundwater, which you can't do anything without. So we have two types of forces. Two types of forces. We have two types of forces. We have the body force. Yes.
Look, I have a question.
Yeah, go ahead.
Yeah, so what I get is all these applies to in situ material. But then how does this also apply to areas like tailings dam that are constructed and the slopes need to be stable?
Okay, so I think we talked a bit about some of these as in when we were to talk about limit equilibrium and what's the name? Water content, plasticity, and whatnot. So usually if you want to talk about if you get to understand the various properties of the rocks you are going to dam, already these ones have got what's the name? They have already gotten fractured and you are transporting to a place. So you need to understand the angle of repose of the material so that you can batter the angle very well. So when it comes to the dams, usually it is about the angle of repose of the material and as to whether the material is capable of weathering easily. How durable is the material? So if you get to know the durability of that material, how it's going to react to weathering. Is it going to weather fast or slowly? If you get to know some of these properties of that material you are transporting to your waste dam, then it will help you batter the waste dam very well and get good slope angles over there, and that will ensure safety. So although we are talking about these ones within the pit, but then there are certain aspects of it you can also apply when you get to the dams. Unless those of us in the field also have got something to add to that.
Doc, if I can come in.
Yeah, go ahead.
Yes, and also when it comes to TSF design and construction as well, you also need to understand the foundation on which you are putting up your embankment, because that will set the base for whatever embankment you are placing on. So the foundation, the material properties, so that you can get the required compaction to set the structure on.
All right. Thank you. So, Danny, are you okay?
Yes, thank you, Doc.
All right, you're welcome. Thank you, Mr. Ajiman, for that contribution. All right, so we are talking about stresses. Right from the beginning of this program, we have talked about stresses here, stresses there, because that is the main thing that we are going to subject our rock to. This stress may be in the form of the impact that this blasting is going to have on the rock. It may be as a result of the trucks moving. It may be as a result of the waste you are going to dump at a certain place. It may be as a result of you pouring some wastewater. Maybe you have an abandoned pit, although you are no longer working there, but you tend to pump water into that pit. Fine. It's an abandoned pit, but what happens when it fails? For example, a dam fails. So all these things are forces you are, or stresses you are subjecting the rock formation to. And so these forces or stresses have been classified as body force and then surface force. And what is a body force? So I have earlier on established that the rock formation already has got its internal forces. Just like you as human being, you have got what you already are thinking about. And depending on your situation at any given time, other things have come to add, which keeps you thinking how to get out of it. And so you already have a situation you are battling with, and then another comes to join. So every body has got, the rock itself has got its force that exists within it. And then you have the surface force, which now are the external features or the external loads we are applying, the stresses we are going to apply as individuals as a result of our activities. So the external surface of a body and the results from physical contact with other body. This is what we call the surface force. So the term stress, as already established, is force per unit area. And the rock specimen having geological discontinuity, such as the joint, when underloading system occurs or causes what sliding along the discontinuity. So the shear stress required causing sliding increases with increasing of the normal stress. The shear stress required causing sliding increases with increasing normal stress. So if I apply a particular stress, okay, the normal force that I'm going to apply to something, then I need to increase the shear strength of that particular body to oppose the external force you are applying to it. Then, so if there is that discontinuity within, we say that then the shear strength must be higher enough to resist these external applications or the deformation that is likely to occur. So the slope of a line relating to normal stress, which is this sigma and tau, and then you have your internal angle of friction. These are the things. So the slope of a line relating to normal stress, the shear stress, and these are the things we made mention of when we're talking about the Mohr circle, okay, this thing. So that is what we are referring to. So you need to know your phi here, which is the internal angle. You know this, and then your normal stress. These three parameters must be known. then finally you can get the cohesive force that exists within the material to avoid the sliding. So if the discontinuity surface is cemented or it is rough, a finite value of shear stress will be required to cause sliding when the normal is 0. Then the initial value of shear stress defines the cohesive force of or strength of the material, and the relationship between the shear stress and calculation of normal stress is shown in these figures. So these were the things we talked about initially. So we have, assuming I have this as a block, and then I'm applying some kind of external force on it. There should be an opposing force that will prevent this block from moving. And so if I increase this shear stress that is causing the sliding, then the normal stress must also be increased to avoid the movement in this direction. Whilst I expect that the resistive force within this particular block must also be high. So for shear strength, if I'm applying a shear stress, then the shear strength must be higher. So the stress is always what you are applying. So take note of this. Stress is the external force you are applying, and the strength is what exists within the formation. So this formation, which is the Mohr circle we drew earlier on, is what we used in obtaining this particular Mohr circle is what gave us this type of graph we already have.